ನನ್ನ ಹತ್ರ ಇದೆ ಬಿಡೋದು.
No, mic and speaker. Mic and speaker should not near. It should not be near.
Good afternoon. In this lecture, we will essentially discuss some background cosmology and importantly, understand as to why we need this epoch of inflation. There are many ways of understanding why we need this epoch of inflation, and I will try to describe at least one of them. And then we will discuss more as we proceed. So this lecture 2. We will start with we'll first arrive at the FLRW metric. It's the Friedman, Lemaitre, Robertson, Walker metric. This is the line element that describes the expanding universe. I'm assuming some of this information you already know. And then we will discuss kinematics in an FLRW universe. In particular, we will see that photons redshift. I would urge you to work out the corresponding result for the case of massive particles, because I need the notion of redshift, and to make progress, to discuss a few points. And I will solve the geodesic equation that describes photons. Then we will talk about dynamics. I discussed in the morning as to how there is matter present, there is radiation present. We will ignore spatial curvature for most of our discussion. And as we make progress, we will try to justify why we live in a reasonably close to spatially flat universe through inflation. And we will just focus on the dynamics during the radiation and matter-dominated universes. And earlier, during a little later, during inflation and reheating. And then, we will discuss why we need inflation. And here, when we discuss the dynamics, I will discuss what are known as cosmological parameters. I will introduce the cosmological parameters. We see that the universe is homogeneous and isotropic. Okay. And we are going to describe the universe from a special class of observers. The universe is expanding. We are sitting in a galaxy which is co-moving with the expansion. And we are describing a universe in this frame of reference. And we want to write down the metric in that frame of reference. And it is in this frame of reference that the universe is homogeneous and isotropic. If I send a spacecraft from here to Andromeda, in that frame of reference, the universe is not homogeneous isotropic. There is evidently a direction corresponding to the motion of the spacecraft. A generic metric, I'm learning to use this space, okay? A generic metric can be written in this form. Before I write that, a couple of conventions I realize I need to include. I'll work with C equal to 1 units. When I need to generate perturbations, etc., I need quantum mechanics, quantum field theory. I will later set h bar equal to 1 as well. And MPL squared, Planck mass, will be 1 over 8 pi g, g being the gravitational constant. So we are writing down this metric. Consider the most generic form of the metric. Let me write minus g00 dt squared, right? And then plus some 2g0i dxi dxj. Another convention, mu nu will go from 0 to 3, and ij, etc. The Greek indices go from 0 to 3, and the Latin indices will be from 1 to 3. So this is the sum over the spatial part. And then you have a spatial metric sigma ij dxi dxj. This is the most generic form of the metric, that I can write down. I haven't yet said anything about cosmology or any specific space-time. Sorry? Yes, I made an error. Yes, it should be dt dxi. Thank you. And now, this is, can you tell me the nature of this quantity? What kind of mathematical object this is? It's a vector. It has one free index, right? And we just agreed that, the universe is homogeneous and isotropic. And if you want the universe, you want to describe a universe, right? You can't have a G0I. And again, I'm emphasizing we are describing the universe in certain frames of reference. And these frames of reference are co-moving observers who are moving with the expansion of the universe. There is another thing which I can quickly converge upon, right? If I talk of an observer who's dxi is 0, okay, then what will happen is that this will be 0, and ds squared is g00 d tau squared, dt squared rather. And I can write ds squared as d tau squared, tau being the proper time in the frame of that observer. Okay, I'm choosing that to be the cosmic time. In other words, t I have written is tau in this observer who's sitting on a galaxy and taking part in the expansion. Okay, in other words, I'm setting g00 to be 1. So my metric reduces to minus dt squared plus sigma ij dxi dxj. Now it's a matter of dealing with this metric, what this line element is. I need to account for the expansion of the universe, and I need to account for, what else do I need to account for? I need to account for the expansion of the universe, and I need to account for homogeneity. Homogeneity represents space, right? And you want to represent homogeneity in a coordinate independent fashion. One of the ways of describing that is claiming that the scalar curvature is independent of space. So remember, we have some time coordinate, okay? There are no cross terms, there are no G0 dxi dt terms, because otherwise it will correspond to some velocity. Remember, if you have a rotating object like a black hole or something, there is a dt d phi term. No such things can occur in cosmology if you want to describe a homogeneous isotropic universe. And you're left with to calculate this. Now, there is an exercise in GR which says that if you have a space or space-time of constant curvature, its Ricci tensor or Riemann tensor can be completely expressed in terms of the metric. I'm going to make use of this. I'm going to list this as an exercise. I would urge you to read up, textbooks on GR will illustrate this, okay? So what you can do is as follows. You can write R, A, B, C, D as follows. Kappa, sigma, AC, sigma, BC, BD, minus sigma, AD, sigma, BC. Is that clear? Okay, I will leave this as an exercise for you to prove. Okay, I'm not able to immediately mention a reference. I can mention it later. Okay, so what do I have? Then it immediately, you can construct RAC, right? Okay, which is nothing but sigma BD, RABCD, okay? And you can show that, right? This happens to be, okay, 2 kappa sigma AC. There are steps, intermediate steps. I'm not filling in for want of completeness. I'm sorry, for want of time. You need to complete them, okay? There are exercises. Wherever I write exercise, you need to complete them, okay? So what have I said? I'm trying to describe the metric on the three-dimensional surface. I know it is homogeneous, and I want to characterize in an invariant fashion, and which means that the scalar curvature has to be a constant. And that's determined by kappa, which is a constant. Okay. And in spaces or space-times with constant curvature, the RABCD can be written in this form, where sigma is the metric of this surface, of this three-dimensional surface in this context. But I'm sure you know other, surfaces with constant curvature, such as the surface of a sphere. You can convince yourself that this is true. So now, which means, and you can immediately show what happens to R. R is just sigma AC RAC, right? Which means 2 kappa sigma AC, which is what? Is 6 kappa, because we are in 3 dimensions. Okay, that's what it is. Now, what it means is that you know RAC in terms of sigma AC. Remember, we are trying to construct this 3-dimensional metric tensor. Now, we need to write a form of the metric which reflects the homogeneity and isotropy. Okay? And it's not difficult to guess this form of this metric. Okay? You can write a metric of the following form. Okay? Remember, we are interested in only the spatial part. Let me call this, for convenience, as dl squared, right? Okay? And this happens to be e power lambda of r dr squared plus r squared d theta squared plus sine squared theta d phi squared, right? Homogeneity, right, implies spherical symmetry, and therefore I can write the most generic spherically symmetric metric in this form. That's all there is to it. There are some more exercises for you to fill in, okay? What you need to do is that you need to calculate RRR, okay? The Ricci tensor, and that happens to be 1 over r d lambda by dr, okay? R theta theta, which is e power minus lambda of r, minus 2 plus 2e power lambda. Okay, I think it's e power lambda of r, okay, plus r d lambda by dr, okay, and r phi phi, okay, happens to be e power sine squared theta r theta theta. That's all there is to it. Okay. Right. That's all there is to it. I hope it's clear. So what I have made use of here is in spaces of constant curvature. Actually, it's true in spaces or spacetimes of constant curvature. Okay. Spaces of constant curvature. This relation holds true. I've just made use of it. And you know the components of the metric tensor. Okay. So what you have are, when you use that relation, you have these following conditions. 1 over r d lambda by dr, which is this guy, okay, equal to what? The zeroth component, okay, which should imply this is 2k, sorry, not zeroth component, the grr component, it has to be 2k, right? What else should it be? Sigma AC. What is sigma AC? E power lambda. Okay, I'm suppressing the dependence on r. And similarly, you can show that e power minus e power lambda plus 1 plus r by 2 e power minus lambda d lambda by dr equal to 2k r squared. Okay. And the other thing is not an independent equation. You're left with these two. Okay. You can integrate this to obtain lambda of r. I will leave this as an exercise again. Okay. To make progress, I have to give you exercises, and you arrive at the familiar Robertson-Walker metric. I will write that metric in a matter of minutes. But what I need you to appreciate is that I could have multiplied this k with any quantity that depends purely on time. And all this analysis would have gone through, because this depends on only r theta phi. Thereby, you arrive at the line element of the FLRW universe. Okay. So what do you have? You can integrate this to obtain okay, integrate them to obtain that e power lambda is equal to 1 over 1 minus kappa r square. And that leaves us this FLRW, FLRW line element. Right, which tells you that ds squared is minus dt squared plus a square of t dr squared by 1 minus kappa r squared plus r squared d theta squared plus d phi squared. That's the form of the line element we work with. And this is the spatial curvature, right? As you can see. And again, all I have done is that multiply the sigma ij by a square of t. And this a square of t is what is known as the scale factor. How do I know what is kappa? What is the dimension of kappa? 1 over length squared. It tells you the curvature of your space. How do you determine kappa? You need to determine by observations. And we'll talk about what's the value of kappa very soon. And what you have, this describes an expanding universe. So you can think of the galaxies as, think of a grid, right? And each point in the grid containing a galaxy. The grid doesn't end. It ends in all directions, extends in all directions. And the grid itself is expanding. The locations of these galaxies are changing with time because of the expansion. But if a galaxy is located at 111, it continues to remain located at 111. But the distance between 111 and 000 is changing with time because the grid is being stretched uniformly in all directions. And that's what is described by the scale factor. So this is as far as the line element is concerned. We need to quickly move on to understand kinematics involving photons. Again, I'm assuming that you know GR, which means you know things like the geodesic equation and Einstein's equations, all right? And so we need to write down the geodesic equations for photons. And our primary result is the primary goal is to help us understand how does the frequency of a photon change with time or scale factor. And let's do that exercise. Okay, I keep looking for my glasses there. Right. So what we are going to look at is essentially the zeroth component of the geodesic equation. Let me remind you the geodesic equation. You have d squared x mu by d some lambda squared. Remember, I can't define a proper time for the photon. So I use some other affine parameter to describe the trajectory of the photon plus gamma mu alpha beta u alpha u beta equal to 0, where u alpha is dx alpha by the same lambda d lambda. And what is gammas? Gammas are the Christoffel symbols. So another exercise, okay, where you go, given this metric, calculate everything, okay? You calculate, I would urge you to calculate gamma alpha beta delta, okay? And R alpha beta mu nu, R alpha beta, okay? R and then G alpha beta. All of these will require as we proceed, okay? In fact, I will use it very soon to write the dynamics of the Friedmann universe. So there, in addition to this, there is also the equation that u alpha for a photon is 0, okay? So what are we interested in? So I would urge you to calculate this, okay? And if you look at the 0th component, that is mu equal to 0, what you obtain is the following. Maybe this will not be enough. I'll move to the next part of the board. So what do I have? I have d square t by d lambda square plus A dot by A, 1 over 1 minus kappa R squared, right? dr by d lambda whole square, okay, plus R squared d theta by d lambda whole square, right, plus R squared sine squared theta d phi by d lambda whole square equals 0. Okay, this is what I want. Yes. This is A, not Q. Is dx alpha by d lambda. Yes. No, I can't use a proper time for the case of photons, and therefore I use another parameter, some arbitrary parameter to describe the trajectory. Okay? All right? Okay. So what do I have? Now this happens to be, you can write this as ui, okay? All right? Into, this happens to be ui divided by a square. That is sigma ij, uj, all right, by a square. And as a result, what do I have? I can write this as d square, okay? That's the first part. And then I use this condition, u alpha equal to 0. What does it imply? It implies u alpha equal to 0 implies minus dt by d lambda whole square, okay, plus ui equal to 0. Okay, or dt by, sorry, this should be lambda, or dt by d lambda whole square is equal to ui. Something I didn't mention when I mentioned the conventions, but I presume it's evident. I'm working with metric such that the metric signature is minus plus plus plus. Okay, and I presume you recognize that. So if you plug this in, here, what do I get? I get the following. I get d squared t by d lambda squared plus a dot by a dt by d lambda whole squared equal to 0, which I need to integrate. And what I am interested in, okay, and I want you to appreciate is the following, okay. Note that W is dt by d lambda. It's not W, it's omega. Okay, what is omega? We are talking about photons. Omega is the frequency, or with modulo constants, it's the energy of the system, okay? And energy is nothing but the zeroth component of the form momentum. Okay, I'm defining the form momentum with respect to lambda. Okay, form momentum is just, modulo constants is dt by some affine derivative of some affine parameter, which I've chosen to be lambda. So this is what it is. So therefore, I can write this equation as dw by d lambda whole square. That's right. Okay, dw by d lambda, that's it. Okay, I can write this equal to minus dA by d lambda, right? D lambda by dt into 1 over A. Okay? All right. Now I have missed something. This is d omega by d lambda, all right, is equal to, there is something I missed out. Just give me a minute. This is d omega by d lambda divided by, if I bring this, dt by d lambda whole square, okay, is minus dA by d lambda, 1 over A, okay, and then d lambda by dt. Okay, I can strike this out. Okay, if I'm making some errors in the algebra, kindly bring it to my attention. So what do I have? I have the following. So what do I have here? I have the following, dw by d lambda, right, divided by d omega by d lambda by omega equal to minus dA by d lambda into 1 over A, or I can arrive at it as, what do I have? Okay, d double omega by omega is minus dA by A, or omega is proportional to 1 over A. Okay, so what I have shown is that, if you have a photon propagating in an FLRW universe, its frequency changes with time in that fashion. I hope you recognize if I leave a photon in this expanding universe, its frequency will automatically redshift independent of what the source is, and it'll go as 1 over A. Okay, and this is what causes the redshift of spectra of galaxies. And at some times, we will indeed talk different epochs in terms of redshift. Yes. This one. Right? Okay, that's what it is. Instead of p mu is m squared, I've used u mu is 0. Okay, so again, to emphasize, we have derived the form of the Friedmann line element by starting with the fact that we are in a homogeneous and isotropic space-time. And then using the line element, we have arrived at the fact that the frequency of photons redshift as 1 over A. If you leave a photon, I'm repeating myself for emphasis, if you leave a photon in a Friedmann universe, its frequency will redshift independent of its trajectory. Okay, whatever be its motion, its frequency will. Okay, I should know not whatever be its trajectory. It is moving on a geodesic. If you leave a photon alone, okay, its frequency or energy will redshift. Yes. So I have just written A dot as dA by d lambda, dA lambda by dt. Yeah. Okay. So next, now we need to move to the dynamics of the Friedmann universe. Okay, and in order to do so, we need to write down the stress energy tensor associated with the matter fields that are present in the universe. Okay, I will come to that in a minute. So what is the dynamics governed by? It is governed by the Einstein's equations. This duster doesn't erase this very well. So what do you have? You have G mu nu equal to 8 pi G T mu. 8 pi G T mu nu. That's right. Okay. And what you need to do is you need to calculate the G mu nu. Remember, amongst the very many quantities that I want you to calculate, you would need to calculate this. You can write a mathematical code to do so, or you can use more sophisticated software like Cadabra, which will just quickly calculate them for you. Whatever it is, calculate them. Now, we need to specify what is T mu nu. I hope you have learned some classical field theory, okay, where you have written the stress energy tensor. We can think of matter and radiation present in the universe as fluids. If you have a fluid, what should the fluid be described by? What should the fluid be described by? Sorry? There will be density, okay, and then there will be pressure, right? And that's it. Velocity, I can combine them to write a 4 velocity u mu. Okay, all right. And the stress energy tensor of ideal fluid is given by the following expression. Let me pull that out. Where is that? I just want to get the sign right, overall sign right. Yes. Okay. So the T mu nu is rho plus P u mu u nu, okay, plus P delta mu nu. Okay, this board is making it difficult for me to write. Okay, T mu nu is rho plus P u mu u nu plus P delta mu nu. Rho and P being the pressure, matter density and pressure, and u mu, as I said, is the 4 velocity. Now, we know the G mu nu, right? Well, you are supposed to calculate it. Given the line element, you can calculate the G mu nu, okay? But we need the T mu nu, okay? In what frame do we specify the T mu nu? In the same frame, you have calculated the small G mu nu, the metric, and you're going to calculate the capital G mu nu. This is in the frame of the observers who are co-moving with the expansion. All right? So think of, so there is matter distributed in the universe. Think of massive particles present everywhere in the universe. And, this massive particle is co-moving with the expansion. In such a case, what is U mu? 100, okay, 1000, okay? And therefore, all right, so what you have is as follows. The stress energy tensor reduces to this following form. In that frame, in a, where U mu is 1000, the stress energy tensor reduces to minus rho, its diagonal, P. This is not surprising, okay? Because if the zero I components are non-zero, what does it reflect? It reflects a vector. It reflects a current flowing in some direction. Remember, in the context of an electromagnetic field, do you know what is the T0I component? It has a name. Pointing vector. What does pointing vector tells you? The flux of energy being carried. Okay, so the fact that there is nothing being carried is consistent with the fact that you have a universe which is homogeneous and isotropic. Okay, and that reflects the isotropy, and this also reflects the isotropy, the fact that the pressure is the same in all directions. So now you need to write down the Einstein's equations. As you may have guessed, it is only the 0 and the ij components of Gij that are non-zero, and you can plug that in and arrive at the so-called Friedmann equations. So let me write them down for you. Okay, so what you have is as follows. Okay, the 0 equation leads to, I will explain this, h squared by k by a square equal to 8 pi g by 3 rho. These are the Friedmann equations. Okay, and then the second equation, oh my God. Is, I don't, 2a double dot by a plus a dot squared by a plus k by kappa by a squared is minus 8 pi gp. All right. Now, here you have three quantities, and I should mention what this h is. H is a dot by a, and dot hereafter will denote differential with respect to the cosmic time coordinate. Okay, these are the Friedmann equations. You can arrive at it. You know the T mu nu. You need to calculate the G upper and lower mu, okay, the mixed tensor, and equate it to this T mu nu, and you will arrive at these two equations. All right, and where capital H is called the Hubble parameter, it's a dot by a, and the dot, I'm repeating, denotes differentiation with respect to the cosmic time. There are two equations. How many unknowns are there? What are the quantities you want to determine? What are the quantities you need to determine? A, rho, and P, right? There are three unknown. Well, do you have any other equations? Sorry? Loudly, I can't hear you. The conservation of the stress energy tensor, okay? So what does this mean? T mu nu semicolon mu equal to 0, okay? I'm going to give you another exercise. I can't be solving all of this for want of time, okay? So what is this? This implies rho dot plus 3h rho plus p equal to 0. Okay, so in principle, you have the third equation, but that not quite. those two equations can be combined to arrive at this. This is not an independent equation. Okay. All right. So it is not an independent equation, just follows from these two equations. So what do you need to do? You need to make some assumption. And you assume there is an equation of state describing the fluids. There's an equation of state describing the fluids. Let me get another chalk piece. So what you do is as follows. You assume P equal to W rho, where W, this is W, not omega, is assumed to be a constant. Right? And what you have is the following, okay? You can have W equal to 0. This corresponds to ordinary matter, okay? What is often referred to as non-relativistic matter. Okay, and you will have W equal to 1/3, which corresponds to radiation, bath of photons. Okay, now you can combine these to solve for A of t. Now what you do is as follows. We are interested in the dynamics of the Friedman universe. What it means is that we want to solve for A as a function of time. How does A behave? Remember, that's the only unknown in that. Well, there is another unknown. What is it called? Kappa. Okay. All right. So what we are going to assume is that what does kappa represent? It represents the spatial curvature of the universe. It's a constant. Often kappa is assumed to be 0, where the spatial curvature is 0, or the spatial part of the universe is flat. Space-time is not flat. It is just the spatial sections corresponding to constant time surface of this FLRW universe are flat. So you assume, or kappa can be positive or negative corresponding to closed or open universes. For all our discussion here, we are going to assume that the universe is spatially flat. Okay. There are reasons to believe it. The CMB data points to a spatially flat universe. Whether there are deviations from it are being examined, but many people believe that CMB data points to a spatially flat universe. I will state that point in a slightly different fashion as we proceed. Yes. Did I write? Yes, it should be 1/3. Okay. No one is pointing out the error. Okay. It should be 1/3 corresponding to radiation. If you don't know how that arises, please speak to me. I can provide you proofs. So what we are going to work with is a spatially flat universe. Which corresponds to kappa equal to 0. Okay. Now, what are we going to do? Under these conditions, we would like to solve for A of t. Okay. What are we left with? We are left with this. A dot by A whole squared is equal to 8 pi g by 3 rho. Okay. And this contains a second derivative. I don't want to go around solving that. I will solve this instead. Okay. And I will solve rho dot plus 3h into rho plus p equal to 0. And it is, I should emphasize, this is true whatever the value of kappa. Okay. So some part of the result is true for whatever the value of kappa. So now this implies I can write this as W1 rho. Yeah. Okay. So what do I have? D rho by dt is equal to minus 3 A dot by A into 1 plus W. Okay. All right. So what does it imply? Yes. Into rho. Yes, that's right. Thank you. Yes, just give me a minute. I'll complete this one step and come to you. Unless I have made an error. Okay. So I can immediately integrate this to obtain rho is proportional to It's a first order differential equation. You can immediately integrate to obtain. So I can write this as dA by dt by A, right? The dt I can just cross out to say that, okay, the rho I can bring it down. Rho is proportional to minus 3 into 1 plus W. That's the result I want. Yeah? Okay. Was that a question or comment? Yes. Right. The spatial curvature, if you recall, the three-dimensional spatial curvature was proportional to kappa. So it reflects the curvature. We wrote it in terms of the metric. It happens to be a constant. The spatial curvature of the segments, because the space-time is the spatial part is homogeneous. Space-time is homogeneous. And if you want to say that, in a coordinate invariant way, I will say the scalar curvature is a constant. It's independent of space. Remember, I'm describing the spatial part of the complete line element. Have I clarified that, Abhishek? Okay, you can ask me again after the lecture. Okay, so this is what it is. So when W equal to 0, what do you have? Rho non-relativistic, right? Is proportional to a power minus 3. Okay, and when W equal to 1/3, rho relativistic, this goes as 1 over a power 4. Okay, so what we see, something I said in the morning, you can use general relativity to show that as you go back in time, what it means is that the scale factor decreases, the energy density in the radiation grows faster than the energy density in matter. Okay, one very hand-waving way of thinking about it is as follows. If you have a collection of particles, massive particles, all that happens when the universe expands is that its volume goes like a cube. Right? So the number density falls as 1 over a cube. So the energy density of non-relativistic matter is number times mass, number density times mass. So it goes as 1 over a cube. In the context of photons or radiation, okay, what do you have? You have number density times the frequency of the photon or the energy of the photon. Number density does go as 1 over a cube, but the frequency also goes as 1 over a, and therefore the whole thing goes as 1 over a power 4. And if you have thermal radiation, why are we interested in thermal radiation? If you have CMB, right? What do you have? You have rho radiation proportional to, if you have a thermal radiation, there is a famous law called the Stefan-Boltzmann's law, which tells you that sigma rho r is proportional to T, some sigma T power 4 is proportional to T power 4. So the temperature of the radiation goes as 1 over A. This is one of the things I said in the morning, that if the temperature is 3 Kelvin today, when the universe was 1,000 times smaller, the temperature is 10 power 3 times 3 Kelvin, which is 3,000 Kelvin, which is roughly the temperature at the time of decoupling. Okay, so as you go back earlier in time, the temperature of the universe keeps rising, and the universe becomes hotter and hotter. Now we need to plug all this in our Friedman universe. Okay, yeah. Of non-relativistic matter. Okay, I am not able to, no, I'm not able to immediately comment about it. I understand what you're saying. It goes as 1 over A squared, right? Okay, I need to think about it and comment. Okay, so what will happen is that when you, there is an exercise I can give you, or you can find it in a text. If you calculate, what are you interested in? You have a collection of massive particles in a thermal bath, right? There are 2 scales involved. What are the 2 scales? Mass and temperature, energy scales involved. There are 2 regimes. One, when the mass is much larger than the temperature, or the other way around. When the mass is much larger than the temperature, you can show that rho is proportional to n times m, n being the number density and m being the mass. In the other extreme, you can show that rho goes as T power 4. Okay, the temperature of very massive particles, I'm not able to comment at this stage. I need to look at it and comment. I know there is a relation. Okay, are there any other comments slash questions? Okay, so what I'm going to do now is that I have, there are some things. So I haven't completed this exercise. What is that we need to do? We have just obtained the behavior of rho, right? I need to substitute. We have solved this equation, right? I need to substitute this here. We are not interested in this equation. Anyway, only two are independent. I don't want to deal with second derivatives. Okay, I know how rho behaves, and therefore I can obtain H. So consider a situation, okay? It's called a matter-dominated universe, okay? Kappa equal to 0, we have already assumed, okay? All right, and then what do you have? You have A dot squared by A square is proportional to rho non-relativistic. Universe is dominated by matter, it's flat. So what do I have? Okay, I can erase this, write it as 1 over A cube. So this is A. So what do I have? A dot squared is constant, right? So A goes as T power 2/3. I will let you work that out. Okay. So in a matter-dominated universe, right, A goes as T power 2/3. And similarly, in a radiation-dominated universe, what will I have? If I write the same equation, A dot squared, kappa equal to 0 again, okay? A dot squared by A squared is proportional to 1 over A power 4. This is squared. So is A dot is proportional to constant. Okay. So A is proportional to T power half. I don't know whether you're able to see that. I will try to write it here. Okay. So in a radiation and matter dominated universe, A goes as T power 2/3 and T power half. Okay. Let me summarize, write it here. Matter domination, A is proportional to T to power 2/3, and radiation domination, T power half. This is in situations. What are you assuming? We are assuming kappa equal to 0. Okay. We have in principle solved the equations and arrived at how the scale factor behaves. Okay. But it is convenient for us to include everything and introduce what are known as cosmological parameters. This is just to get an idea of how the scale factor behaves in different epochs. You can, for instance, if you have a cosmological constant dominated universe, okay, I erase there is this equation. If W equal to -1, what happens to rho dot? Rho dot is 0, okay, or rho is a constant. That's what is referred to as a cosmological constant, okay? In a cosmological constant dominated universe, what will I have? A dot by A will be a constant. What will A be? It will be an exponential functions, okay? The universe will go through accelerated expansion. A double dot by A, A double dot is always positive. You're differentiating exponential, okay, with a coefficient which is positive, it will always be positive. And we will see later, what we will refer to as a de Sitter solution, okay? All right, we'll come to that later. So this is a good time to introduce the notion of something known as cosmological parameters. Right? Okay. So what I'm going to have is I'm going to go back to my equation, 8 pi g by 3, and rho I have. Okay. I'm going to include everything possible. I have rho nr, okay, rho r, okay, rho lambda. And I'm going to include even kappa. Equal to this. So in principle, I've included everything. Okay. And I'm going to rewrite this in the following fashion. Okay. All right. So I can write kappa by A square is equal to 8 pi g by 3 rho minus h square. The rho is the total rho, sum of all these things. Okay, I hope it's clear. All right. So I'm going to introduce something called rho c of t, which is 8 pi 3h squared by 8 pi g. So what happens when rho equal to 3h squared by 8 pi g? You can see that this term cancels. Okay, so this is a critical density at which kappa is 0. Okay, and that rho c, it's called the critical density. It's a function of the Hubble parameter. And remember that, okay, I when introduce omega, I need to introduce that now. I thought I have written it down. Right. So what do we have? I'm going to introduce this quantity called omega of t, which is rho by, which is a function of time. Rho is a function of time divided by rho c of t. Okay. Therefore, kappa by a square x square is equal to omega t minus 1. Okay. All right. So what it implies is that omega equal to 1 if kappa is equal to 0 at any times, at any time. Okay. Right. So what I'm going to write this in this fashion. If this is the case, kappa equal to, we will need this equation, make a note of this. We will need this much later when we discuss inflation. Okay, minus 1 a square x square. Right? Okay. I'm going to introduce a notation. This is equal to omega naught minus 1 a naught square h naught square. I will explain what I have done. This is a constant. I can evaluate it at any time. Okay. This omega is a function of t. Right? I choose to, the knots correspond to their values today. Okay, because if I calculate the total omega today, what is omega? Omega is rho by rho c. Okay, I can maybe compare, measure what is omega naught today. Okay, and I can measure a naught and h naught. In principle, these should be, I can choose to evaluate this at any time. And as a result, I can write kappa by a squared as omega naught minus 1 a naught square h naught square divided by a square. Have I got that right? Yes. Okay. So I'm going to use this information and plug this in here. Okay. And what I'm going to do something here now. Recall how does rho nr behave? Rho nr goes as 1 over a cube. So I can write this as rho nr a naught by a cube. Is this clear? What I've done? Because rho nr, non-relativistic matter, goes as 1 over a cube. And at a equal to a naught, it is rho nr. I've just included that. And here it is a naught by a power 4. And this is just rho nr lambda naught because it doesn't change with time. That's all there is to it. So I can plug this in. And what do I have? I have h squared. I'll take this kappa by 8 pi g by 3. Right? So rho nr naught a naught by a whole cube plus rho r naught a naught by a whole power 4 plus rho lambda naught. What else do I have? Minus omega naught minus 1 a naught square h naught square divided by a square. Okay, I'm dividing everywhere by h naught square. Okay, I've divided this by h naught square, h naught square. Okay, and what is this guy? What is this guy? 3h naught h squared by 8 pi g is the critical density. It's the critical density evaluated today. Okay, rho c naught. So 1 over rho c naught. So therefore I have rho c naught, and rho c naught. So I introduce what are the cosmological parameters. Right. So what do I have? I have h square equal to by h naught square, okay, is omega nr naught okay, into A naught by A whole cube plus omega R naught A naught by A whole power 4 plus omega lambda naught minus omega naught minus 1 divided by, where is this? A naught squared by A squared. So these quantities, H naught, omega n r naught, omega r naught, omega lambda naught, and omega naught. Omega naught is not independent. It's a sum of all the omega naughts. And they are known as the cosmological parameters. And I have to determine them from observations. One of the games, as far as this are the cosmological parameters that describe background cosmology. Not all of them are required. We will not have time to talk about it. Okay. But these, in principle, have to be constrained from observations. And what I'm going to do now is just list their values. Okay. Amongst these, we know one of them very well. Do you know which one? Okay, CMB, right? Omega R naught is what? Is rho R naught divided by rho C naught. You know what is rho C naught, okay? In principle, you can measure H naught using Hubble's law. I can measure the velocity redshift relation, okay? Velocity distance relation, or equivalently, what is known as the luminosity distance redshift relation. Okay, I don't not have time to talk about luminosity distance here. I can explain in private, okay, and arrive at the value of H naught. And I'm sure you have heard about the fact that identifying what's the correct value of H naught is an issue today, something that is referred to as the Hubble tension, okay? But you know what is rho R naught. I will let you do this exercise, okay? So H naught is usually written in the following fashion. Okay, H naught is usually written in this fashion. Okay, what is the dimension of H naught? What's the dimension of H naught? 1 over time, right? Look at this. It is kilometer divided by megaparsec, 1 over time. Okay, all right. So it is usually written in this fashion, and people are arguing whether small h, it should not be confused with the Planck constant, which we have anyway set to 1. Okay, and people are arguing whether it is 0.67 or 0.72 or 0.73. Okay, and so I just mentioned those values. I'm just going to mention various values that you can calculate. Okay, so what you should show is the following. Right, show that exercises, numbers. Okay, numbers. I hope I can write all of this here. Okay, rho C naught. Calculate this. Show that this is x squared into 1.88 into 10 power minus 26 kilogram minus m minus 3. Show that. Okay. Notice we have set C equal to 1. It is possible in some cases you have to introduce C to get the correct dimensions. Right? So there is no observable involved. We haven't mentioned the value of the observable, small h. Okay? This just follows from the definition of rho C naught, which I've erased. Rho C naught, remember, is 3h naught squared by 8 pi g. Okay. The other thing you can calculate immediately is the following. You can calculate what is omega R naught. Okay. We know that the temperature of the CMB is, right? The temperature of the CMB is 2.725 Kelvin. And you can plug this in and calculate omega R naught. But notice, omega rho C naught contains h squared. Okay, so often what people quote is omega R naught h squared. Now there is another subtle point. I will come to that in a matter. I'll comment about it, and we will discuss this at a later stage. Okay, just let me show that omega R naught h squared. Okay, is 2.48 into 10 power minus 5. Okay, given that the temperature of the CMB is 2.725 Kelvin, show that omega R naught h squared is 2.48 into 10 power minus 5. If small h is 0.7 or so, it's clear that omega R naught is of the order of 10 power minus 3 or so. So what it means is that in this equation, right, in this equation, at current epochs, I can, unless this becomes comparable to this, or rather 1 over this is of this order, okay, at very early times in the universe, this is not going to play a role. You can ignore for today's evolution this, okay? But at earlier epochs, this will dominate and all these become subdominant. Not surprising. We know that at earlier epochs, it is radiation that is going to dominate. Now, this number that I have indicated includes only photons. There is also another radiation-like particles or particles that are present. These are the neutrinos, okay? You will ask me, what is the neutrino temperature? They are in a thermal distribution. They have different number of degrees of freedom compared to photons, okay? And also there is an important difference. They are fermions rather than bosons. So there are factors you need to account for, okay? But importantly, you will ask, what is that temperature? There is a relation. Once you know the neutrino photon temperature, you can determine the neutrino temperature. I will talk about it when we require. I will need it when we talk about reheating. So what people will do is that this R, ideally, I should have said omega gamma naught, which indicates I'm only including the effects due to radiation, okay? You also need to if I want to truly represent it radiation, the contribution from neutrinos, okay? So what do I have? I will just, so I have indicated the value of this guy, right? I have indicated what is the value of this guy. So we need to know what is this and what is this. And of course, what is corresponding total omega. Yes. I'll just complete this, Avi, and then I'll come to you. Okay. Again, continuing with numbers, right? So what one finds is that from CMB, right? Okay, I will give you the exact reference if you want. This is in fact the Planck 2015. You can update these numbers if you want. Data, okay? So what you find is omega B h squared is about 0.0222, 1, 2, 3, 4. In fact, I will not include the errors, okay? Omega C h squared. I will come explain what these numbers, what these notation implies in a minute, okay? H naught equal to 67.26, all right? Omega K, okay, is equal to omega naught minus 1, okay? And omega mod omega K is much less than 0.005, okay? I think with those remarks, I will stop for today. I will explain what this is. Remember, what do we have here? This is omega non-relativistic. We evidently have baryons, right? Which behave non-relativistic, very massive particles. And we are also supposed to have cold dark matter. Various observations, astrophysical observations, rotation curves of galaxies point to the presence of cold dark matter. And this corresponds to the amount of baryons in the universe, and this corresponds to the amount of cold dark matter. This is the value of H naught that I mentioned. So which means small h is about, okay, of course, I forgot the unit. These are all dimensionless quantities. This is Km, second inverse, megaparsec inverse, which essentially means two galaxies that are separated by a distance of 1 megaparsec are moving away with respect to each other at a velocity of 67 odd kilometer per second. And you have this much amount of baryons, this much amount of cold dark matter. There is more cold dark matter than baryons, about 5 times cold dark matter than baryons, okay? And you also have omega, total omega naught equal to 1, which means kappa is very close to 0. In fact, omega naught minus 1, which is omega k, is strongly constrained by a number like this, okay? So in the dynamics, that is why when I solve for A of t, I chose to ignore kappa. And of course, we also need to justify why is omega naught very small today. Okay, and that's often referred to as the flatness problem. We will see. I will probably give it as an exercise. I will not have time to discuss this at length, how inflation overcomes the flatness problem. There are a couple of remarks that I need to mention before I move on. Okay, so if total omega is 1, right, and you can convince yourself if this is the value of small h, this, okay, you calculate the value of small h from this, it is 0.67, plug this in, and total omega naught is 1, you will find that omega lambda is about 0.7 or so, close to 0.7. I will let you do the exact numbers. And these are from the Planck data. There may be minor changes in the Planck 2018 data. So what we have is a universe which contains 70% of dark energy today, right? About 30% of ordinary matter today, all right? Of non-relativistic matter, of which only 5% consists of baryons and 25% consists of cold dark matter. Okay. Now, what we need to understand is what is the background evolution. And importantly, one of the things we need to understand is I talked about modes coming inside and outside the Hubble radius. Okay. And I talked about what a mode is. I will, what we will do as the start of the next lecture, I was hoping to complete it today, is when did a particular mode of a particular wavelength that falls in the middle of the CMB scale leaves the Hubble radius as you go back in time, or it re-enters the Hubble radius as you go forward in time. Those remarks, I will stop, and I'll be glad to answer a few questions. Avi, you had a question. Use the microphone, please.
Shouldn't you take into account the starlight and the light from other galaxies, stars?
You saw in the morning, I showed a picture where I plotted the intensity of all the light in the universe as a function of wavelength. And you find that the CMB dominates virtually everything else. Okay. I'll put the slide somewhere, or it probably is already available on YouTube. You will see that thing sticking out considerably. That was to emphasize the fact that, the light from the stars are completely negligible. The energy from the light from the stars is completely negligible compared to the amount of energy density in the CMB. Any other questions? Yes.
So the 4 numbers that you have listed on the left, are these 4 of the 6 lambda CDM parameters that people talk about?
So we will use the background. We will need the background parameters. For me, I need them for the sake of completeness. The 2 parameters, as far as I'm interested in the early universe, are essentially R and NS. So I will not talk about this much. It's just to indicate what's the background cosmology. Yes, these are 4 of there are 6 total parameters. 2 of them, actually, if you include the tensors, it's a 7th. Without the tensors, there are 2 cosmological parameters to describe to describe the perturbations, and 4 to describe the background. Omega naught is not independent. It's a sum of the other 3. Okay. In fact, what is often used is omega B, omega C. Okay. These are what are known as derived parameters, and something called theta and tau. Okay. It's the angle subtended by the last scattering, by the horizon at the time of last scattering. And tau is called the optical depth. Okay. So these are what are known as derived parameters.
Yeah. So this omega radiation, to get that, I also need CMB observations, right?
I just need the CMB observation. I know the temperature today. I know that very well. I know that parameter very well. I don't need to run it. I mean, I don't need to include it as a separate parameter. I know that very well. Did I answer your question?
Yeah, I mean, I'm confused because to get all these numbers, ultimately, you need to have the CMB spectrum, right? But I always see that omega R is talked of.
No, you are confusing. What do you mean by a CMB? That's the angular power spectrum. Okay, this comes from the observations of the CMB angular power spectrum, not the CMB, intensity as a function of frequency. Okay, that's the angular power spectrum of the CMB. I haven't talked about perturbations. You have to compare the perturbations with the primordial perturbations, okay, are described by essentially 2 quantities, okay. It's a parameter, but we know its value. That's all I'm saying. Yes? Can you speak loudly?
When we put the homogeneity condition, shouldn't we expect isotropy to be a consequence of that? But instead, we first put an isotropy by removing the I0 component, making it 0, and then we do the homogeneity.
So I think if I recall correctly, isotropy about 2 points is adequate to ensure homogeneity, but we are observing from 1 point. Okay. Right. Okay. So, but we are observing from 1 point. So I have to use them independently.
Okay.
Yeah. Yes, Ratul. So can you just use the microphone, please?
The derivative of Hubble parameter.
Oh, there are. Okay. Yes. I mean, there is, I forget, there is, what is it? Deceleration parameter. There is, there is a jerk, strange names and so on. Okay. And you can introduce them. You can introduce them and try to constrain them. But you are constraining only the value of the Hubble parameter today in this. That's all.
So there are few questions online. We'll just take it and wrap the session.
Sure.
So these are mainly from the morning talk. So someone has asked, what is the K star in the power spectrum? Why do we need it? The pivot scale. You haven't set up the perturbation theory yet. If you are going to cover it then.
So I will talk about it. It is, it's just a convenient, okay. It is introduced because if at K equal to K star, the power spectrum is just AS. And we know AS very well over some scales, which is called the pivot scale, which is typically of the order of about, 0.05 megaparsec inverse or so. So we mentioned that we write the power spectrum in that fashion because we know the value of the amplitude. We can constrain the amplitude of the scalar power spectrum fairly well at that scale. In fact, even the R that I quoted, I don't know whether people notice, there is probably a subscript indicating R 0.002 or something. Okay. It just indicates that we know the value of R at that scale well.
Second question is, does the primordial gravitational waves have an effect or imprint on mu type spectral distortions?
Wow. Okay. I am not able to answer that about particularly mu type. I'm not able to answer that immediately. I do not know. I do not know offhand.
Okay. So the transfer of energy from inflaton field to standard model particles is what gave temperature to the standard model particles and the corresponding particle, SM particles. Is it the picture?
So the broadly, yes. Okay. So what is supposed to happen is that you can transfer the energy. Okay, let me track back. Often you take the entire standard model particles to be represented by some simple scalar field. In the simplest of scenarios, you couple your inflaton to the scalar field, and by the coupling, you try to transfer the energy from phi to chi, say chi being the other field. Of course, you have transferred the energy, but people just, assume that it has thermalized as well. That is a process which I understand is not well understood. It involves microphysics. You need to know, what are the particles present, how are the couplings, etc. So the broad picture of reheating is clear. The microphysics of reheating remains to be fully understood. That has to be modeled in detail, and there can be non-trivial effects.
Is it possible to explain low multipole anisotropy in CMB using inflationary model?
You mean the lower power at the low multipoles?
I presume that is the question, but
Okay.
it just mentions low multipole anisotropy.
So there is, a well-known suppression of power at the low multipoles. Yes, one can construct certain models that improves the fit to a small extent at the low multipoles.
So there is Shayantan Ghosh who has raised his hand to ask question, but we don't have the provision to unmute and broadcast the question. So we can just take it if possible in the chat. Otherwise, we will, you can always, Sayantan, you can always write the question in the chat and we will compile and ask the speaker as during the course of lectures. I hope that is clear.
So he's typing it, is it?
The question is, could you tell what should be the equation of state for neutrino? Should it be 1/3 or 0?
It's 1/3, right? It's relativistic.
Right. So I believe that covers all the questions for the session. We'll close the session for now and reconvene here, same time as morning 11 o'clock tomorrow.
Thank you.